Hello, everyone. Welcome back. Today, we are going to be talking about transformations of exponential functions. So, this is actually very similar to transformations of regular functions, which is something we did last unit. So, let's talk about transformations of exponential functions specifically. So, you may recall that any function can be written in this form here, where we have a, k, d, and c, and each of these has a, for lack of a better term, a function in the function, right? It has a sort of purpose, shall we say, of what it does to the original function. So, for example, a vertically stretches or compresses, and it also reflects across the horizontal axis. So it's a reflection in the horizontal axis or the x-axis in the event that a is negative, right? So if we see a negative a, we know we flip it, right? Then we have k, right, which is inside our function. So part of our exponential in this case is this is an exponential function, and it's a horizontal stretch compression, and also it's a reflection over the vertical axis. So a reflection in the y-axis if this one is negative. Then we have our horizontal shift. So this tells us if we're moving left or right and by how much. And then we have our vertical shift. So if you are unfamiliar with exactly how these work, I do recommend reviewing that last transformations video, as we do go into more detail there, because at the end of the day, this is just another variation of one of the things that we've already done, which is the good news, right? A, K, D, and C are no different now than they were before. It's just a new type of function we're using. Instead of the function being a quadratic, oh, well, now the function is an exponential. So for something to be inside the function, instead of it having to be in brackets with a square root or a square root around it, or a square, or reciprocal, or absolute value sign, or whatever it is, it now has to just be part of the exponent because it's an exponential function. Okay. So here it says each point xy on a parent function can be transformed to a new location using this formula. And this is actually the same formula from previously. This is just review as well. Let's just review. This is our formula that we could use. The first question asks, in words, describe the transformations that have occurred to the following parent functions. So we're going to do that. I'm going to do the first one, and then actually I will show B and C as well, but I do encourage you to pause this and give those a try on your own if you feel comfortable doing so. So for the first one, I'm going to notice that actually, before we do that, let's notice that the original function is 3 to the power of x, and we want to know what's changed, right? What's changed and what transformations would we have to make on that parent function in order to move it to this new function, this y equals 5 times 3 to the power of 2 times x minus 4 plus 7. Okay, so let's do that. So 5 is my a value, and what the a value means is that we do a vertical stretch by that number, assuming it's greater than 1. And this is greater than 1, so yes, or I should say the absolute value of 5, or a, is greater than 1, and therefore it's a stretch, not a compression. So that's my first thing, vertical stretch by factor 5. Okay. The second thing you might notice is the 3. Now, the 3 is part of the original function, it's the base, so this doesn't actually transform it any. This is just a repetition from our parent function. Okay, then we have 2 as our k value, and that means that we're going to do a horizontal compression by factor 1/2, right? Because originally we had 2, and for any k value, we always take the reciprocal, right? Well, we take the reciprocal and the absolute value in order to know what we are multiplying by, right? To know or what our factor is. Okay, then we have 4 right here for our d value, and that means that we will be doing translate right by 4. Now you might see the negative sign and ask, "Oh, why don't we translate left by 4?" And the reason is that negative sign, if we go back to our original equation, this negative sign is already here. We only care about d itself. The negative sign demonstrates to us that we're going right because the negative sign is already part of the equation. So it's always the opposite of what you would think it would be, right? X minus 4 indicates we're going right by 4, and if it said x plus 4, that would actually indicate going left by 4. So it's the opposite of what we would imagine. But however, the 7 is not. The 7 is pretty straightforward. This just means translate up 7. I guess I should 4 units, 7 units, because it's not a factor of 7 or a factor of 4 that we're shifting by. We're just quite literally taking all our values and moving them 4 to the right, then 7 up, and that's what we're doing. Okay, next let's try B. So B says y equals 5 to the power of x is transformed. So what are the transformations? So basically list out the transformations. Okay, so my first thing I see here is this 0.8. So the absolute value of 0.8 is less than 1, so that means we're compressing, right? Everything is becoming only 4/5 or 80% of what it used to be, right? If I used to have 100% and now I have 80%, well, that's a loss, right? I'm compressing. The score is lowering. And I was maybe not lowering by half, right? It could be lowering faster, that's true, or it's not losing most of its value in one step, but it's still compressing. It's still compressed because we're still multiplying it by a fraction that is less than. Okay, so therefore vertical compression by factor 0.8, or you could say 4/5. It doesn't matter. I'm just going to use 0.8 because that's the language they used. I'm going to stick with that. Then I see my 5, which again, the 5 is just a base on our original, so that doesn't actually do anything. That's just a repeat. Then we have our k value as just a negative sign, so that means we reflect in the y-axis. So reflection in the y-axis. Then we have x plus 3, so that actually means that we're going to be moving left 3. So translate left 3. And then minus 6 is translate down 6 units. Good. Okay, let's try C. And again, I encourage you to pause, try this on your own, and then come on back when you're ready. Okay, so for C, it says 0.7 to the power of x is transformed. List the transformations. Okay, so here we have a negative sign for our part of our A, so that already means we're going to reflect on the x axis, or I just said the axis, the x-axis. Then there's 4, so that means vertical stretch by 4, because 4 is greater than 1, right? So vertical stretch by factor 4. Then we have a half here, and remember we always take the reciprocal of k, and the reciprocal of 1/2 is 2, right? So therefore it's a horizontal stretch by 2. Then we have minus 2 here, right, which minus is part of our equation, so it's really translate right 2. Then it's translate up 8. And voila, there we have it. All right, so if the rules made sense, fantastic. If they didn't, or if they were a bit unfamiliar, do review the actual rules, because at the end of the day, this is, if you know the rules, then this is fairly simple. If you don't know the rules, well, then it's perhaps pretty complex. So do make sure that you have those prerequisites down, that you do know the rules for all of this before moving forward. Okay, here we have example 2. It says graph f of x equals 3 to the power of x using at least 3 points. Then write the transformation as an exponential equation. Then graph the exponential equation using at least 3 points. So that's our second thing, is to actually apply this rather than just listing out, oh, what would the transformations be if we were to transform. Here they're saying actually transform. So I'm going to start with 2a and say, well, let's graph those points. So what if we have x is equal to negative 1, 0, and 1. Then we would have 1/3, 1, and 3, right? Because all I'm doing is I'm taking these x values, plugging them in here, and seeing what I get for f of x. So that's where those values came from. So let's put those in here. So negative 1, 1/3, 0, 1, and 1, 3. So there they are there. And voila, just like that, we already completed part A. Now, part B says write the transformations as an exponential equation. Okay? All right, well, let's see what we can do about that. So let's first make it into an exponential equation. G of x is equal to 3 times 3 to the power of 1/2 x plus 4 minus 6. So that's how we could write this transformation as an exponential equation. All I did is I made sure that everything in these brackets of f of whatever it was were inside there, right? We're inside. And that everything else was outside our exponents. So you might notice negative 6 and 3, they're outside the exponents. That's on purpose because they are outside of the function in that transformation, right? In that idea. Good. All right, so now let's graph the transformation. So for this, what I'm going to do is I'm actually going to use this equation earlier, which we haven't used yet today, but it's a very good equation because this allows us to really quickly and easily find these alternate points. So let's make this a little smaller. There we go, and find the alternate points. Okay, so let's start with the first one. Let's do x and g of x, and we're going to plug in all our values. So first we have to find out what the values are. Well, let's see. Looks like a is 3, right? What else do we have? K is negative a half. C, which one's D and C? I forget. C is the one outside. Okay, so it's D first. D would be negative 4, and C would be negative 6. So now all we need to do is take each one of these points and plug them into this equation to get our transformed points. So first I'm going to start with this point here. So I'm going to use this point here of x is equal to negative 1 and y is equal to 1/3. And then of course I'm going to use all 4 of these points as well to get my answer 2. Okay, so let's do that. Let's say x2 is equal to x1 over k. Well, x1 is negative 1 right here, over k, negative a half, plus d, so plus negative 4, comma, and then we have ay1, which is 3 times 1/3, minus 6. So then we have 2 minus 4, 1 minus 6. There we go. So therefore, our first transformed point is 2, -2, -5. So we transformed the point -1, 1/3 to -2, -5. Very good. Okay, now let's do the same for the second point. And I encourage you to pause and try yourself. Let's do the same for the second point, 0 and 1. And of course, we'll use all of these values once again as well. These values stay the same. It's just the points we're actually transforming that are different because we're transforming on the same graph. We're just doing it with multiple points since the question asked us to use at least 3 points. So I'm just going to use the same 3 that we had to use in part A just for simplicity's sake. Okay, so let's do that. We have x1, which is 0 in this case, over k. Well, whatever that is, that's just 0, plus d, so -4. Then we have ay1 plus c, so that's 3 times 1 minus 6. So that is equal to -4. 3 minus 6, which is equal to -4, -3. And there's our second transformed point. Fantastic. And now let's do the very last one, the third transformed point, and then we can graph this. So for this one, it'll be x1, which is 1 over k, so 1 over -1/2. Let's see, plus d, so -4. And then ay1, so 3 times 3 minus 6. So that's equal to -2 minus 4. 9 minus 6, so that's -6, 3. And there's our third point. So now all I need to do is graph those 3 points. And I also might label my graphs as well. That this one, the black graph is representing this one, and the blue graph is this one here, just so we don't get confused. And I didn't label my graph. Okay, so for real, if you're doing this on a test, do label the graph. I didn't bother. We're just going to assume that 1 unit on the graph is 1 unit of measure. But in general, good to label your graphs. Regardless, though, let's do -2, -5 right there, -4, -3 like that, and -6, 3. And then we'll draw that kind of like that. Good. All right, and we have a little extra time. I will actually label a few points on this graph: 2, 4, 6, -2, -4, -6. We'll do 2, 4, 6, -2, -4, -6. Very good. All right, well, that is everything for transformations of exponential functions, specifically with an example. Very good work today, everyone, and we will see you next time. Bye, everyone.